catching all the lights. Just easy as ABC, that's how you make it right.
To the D-A-N-C-E, 1, 2, 3, 4, 5. Sing to the B-E-A-C, get ready to ignite. You were such a BYC, catching all the lights. Just easy.
Section 5.7 is called Modeling Data Using Sinusoidal Functions. So we're going to answer some word problems using sinusoidal functions, and we're also going to do some regression, which we've done a couple times recently. So let's get right to the questions. I've stolen them from your workbook again. So the first one, a nail caught in the tread of a rotating tire traces a path that can be represented by a sinusoidal function. So what this means is there's this tire and it's just rotating in position. There's some nail in this tire. There's the nail right there, and this tire's going around and around and around. I guess I could give some comic book arrows to show it's going around and around and around. And if you think of how high that nail is as the wheel's going around and around, it's up high, and then it gets lower, and then it gets to its lowest point, and then it goes back up to its highest point, and it comes back down. If that doesn't help, I also have this to look at. So you can see here's the nail, that green dot right there, and it's going around and around and around, and the red curve here graphs how high the nail is at any unit in time, and you can see it's going up and down and up and down, and it's a definite sinusoidal function. So Jake and Gilles, I guess that is, Jake and Gilles were given the following information and asked to determine the height of the nail after 6.5 seconds. The tire has a diameter of 50 centimeters. The tire rotates. Well, maybe I'll draw some of this stuff. So we've got our tire, and the diameter of this is 50 centimeters. Whoa, that's not through the middle, but you get the idea. The tire rotates at 10 revolutions per minute. At the start, the nail is halfway between the ground and the maximum height. So at the start, here's the nail. The nail is at maximum height after 1.5 seconds. The nail touches the ground after 4.5 seconds. Okay, let's start with this one right here. The nail rotates at 10 revolutions per minute. What can we tell from that? What we can actually tell is how long it takes to make a single revolution. If it does 10 revolutions in 1 minute, or 60 seconds, how long to do one revolution? 6 seconds. One revolution takes 6 seconds. So what does that refer to? That refers to the period, the amount of time in order for a complete turn of the wheel, or a complete cycle of the sinusoidal function, is 6 seconds. So what I've done here is I put a graph, and because the period is 6 seconds, let's go way out here and put 6 seconds out here. This is our time in seconds, and of course we're going to put 0 here. Alright, the tire has a diameter of 50 centimeters, and at the start the nail is halfway between the ground and the maximum height. Here's the nail right here. So how high is the nail right there? If it's halfway and the diameter is 50, the nail must be at 25. When it's at its lowest point down here, how high is it? Well, obviously 0 as well, it's on the ground. When it's on its highest point, how high is it? It's at 50, so you better put those numbers on as well. Okay, at the start, so it's time 0, the nail is halfway between the ground and the maximum height. So there's the nail at the start. The nail is at its maximum height after 1.5 seconds. So let's break this down. Here's halfway to 6, so this is 3, and halfway between 3 is 1.5, and halfway between 3 and 6 is 4.5, and I think that's all we need. So at the start it's halfway, the nail is at its maximum height after 1.5 seconds, so that's right there. The nail touches the ground after 4.5 seconds. Where do you think it would be after 3? Well, if it's a sinusoidal function, it goes up, then it goes back to here. This is the midline, isn't it? Then it goes down. Where's it going to be at 6? At the midline again. So here is your sinusoidal function. And of course it wouldn't stop there. It would keep going and going and going as time passes, but that's one complete cycle, or one complete period right there. Okay, determine an equation for the height of the nail as a function of time in the form h of t equals a sine bt plus d, where a is greater than 0. Express the parameters as exact values. Okay, by the way, this a is greater than 0. This will always be the case for what we do this year. In pre-calculus 12, we look at when a is less than 0 as well. Just makes it a little bit easier for us. So you'll notice there's no C value. We told you we'd never have to worry about phase shifts. By the way, is there a phase shift in this one? Let's take a look. Remember how you tell if there's a phase shift? What you do is you find the midline. Well, I think it's pretty clear that the midline is right here. That cuts that function in half. And then the only way there's not a phase shift, if the y-intercept of the function goes through the midline, and it does, and then if it moves up to the right, and it does. So there's no phase shift in this case. So what the heck? What does that mean the C value is if there's no phase shift? It means the C value is 0. So what we still need to know is what A is, what D is, and what B is. I'll put B last because that's the hardest one. A is the amplitude. So all you have to know is what the amplitude is. Well, we've drawn the midline. All I need to know is what's this distance right here, or if you want, what's this distance right there. And how much is that distance? From 25 to 50 is 25. The amplitude is 25. The D value. The D value tells you how much vertical shift has taken place. And remember, the quick way to find the D value is just look at where the midline is. So in this case, the midline's at 25. So the D value is also 25. Now, the B value. In order to get the B value, you have to use the equation that the period equals 2 pi over B. Do we know the period? Yes, we do. We already talked about that. The period is 6. If you want, I could write that down. I'll just write it here. 6 equals 2 pi over B. And if you need to solve it this way, you can. Multiply both sides by B. That gets rid of these. So you have 6b on this side, and you still have 2 pi on the other. We want to get the b by itself, so we will divide by 6 and divide by 6. These 6's are gone. What you're left with is b equals 2 pi over 6, but you could cancel those, divide them both by 2, you get pi over 3. Or 1/3 pi, but I kind of like this. Okay, now all you do is plug those numbers into this function right here. So we get h of t equals a, which is 25, sine b, which is pi over 3, t, that's kind of where the x value usually is. Then you put your c value plus 0, but you don't need to put that because it's 0, plus d, which is 25. And there you go. How far to the nearest 0.1 centimeter is the nail above the ground after 6.5 centimeters? So again, there's two ways you could solve this. One way is you could take the 6.5 and you could plug it in here and solve, and the other way you could do it is to graph this. Let's do the plugging in method. So I'm going to start by going pi divided by 3, and then I'm going to multiply that by 6.5. Then I'm going to take the sine value of that, so I'm going to go sine and then answer. So that's second, this one, that gives me the sine value of whatever my last answer was. It's 0.5, oh very nice. Now I'm going to multiply by the 25, and then add 25. And I get my answer is 37.5 centimeters. Nice. So that was Jake's method. Now we're going to do this again, but we're going to use Gilles' method. And what Gilles does is he performs a sinusoidal regression on the data and determines an equation for the height of the nail as a function of time. So he, instead of looking at what the equation is, he's going to use the data. The data he's going to use are these 5 points, 1, 2, 3, 4, 5. It's going to plug those 5 points in and do a linear regression. So for that, let's go to Desmos. Here we go. So we're going to put a table, and if I remember correctly, the times were 0, 1, 1.5, 3, 4.5, and 6. And at the time 0, I remember was at 25, then it went up to 50, came back to 25, went down to 0, and then back up to 25. You can check that, but I'm pretty sure that's right. Now I better do my settings here. My x-axis, I need to go as low as 0 and as high as 6. Why don't I go, I'm just going to leave that for now actually. And for the y-axis, I have to go above 50, so maybe I'll put this up to 70 or something. And can we see all our points there? I see 1, 2, 3, 4. Yeah, I see all my points, so this is good. Now I'm going to do is do a regression. So I put y1, hit my regression button, and I put A sine bx plus c, bx1, isn't it? bx1 plus c plus d, and it should go, and there it is. It's going through nicely. Oh, I can put it into projector mode so it looks even prettier for you, and there you go. I can see all my points, 1 2 3 4 5, and it goes through them perfectly. So if I look over here, it says the A value is 25, the B value is 1.0472, the C value is 119.38, and the D value is 25. So I have to put all those numbers into my equation. So let's go do that. So the equation is y equals 25 sine 1.0472, I probably don't need to do that many decimal points, but whatever, plus 119.38 plus 25. There we go. And now again, we want to know how high is the nail above the ground after 6.5 seconds. So that's my x value, right, times 6.5. So I put in here x equals 6.5. I check to see where it crosses, and I get 37.5. So 37.5 centimeters. So who was right? Jill said 37.5, and Jake said 37.5. They both got the right answer. Isn't that beautiful? It often won't be the case that you get exactly the same when you do a linear regression. The only way that it worked out exact this time is because all Gilles' data points were exactly on the graph. But often with regression, it's not a perfect fit. And then we would have to, what the regression does is it finds a line of, or curve of best fit. And it would be really close, but maybe not exact. But in this case, it was perfect. Okay, the depth d meters of water in a harbor t hours after midnight can be approximated by the sinusoidal function. Here it is. I'll highlight it for us. D of t equals 12 plus 5 sine time blah 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 blah. I'm not going to read all that. Where 0 is less than or equal to t is less than or equal to 24. Why? Why is 0 less than t? Because it's talking about the water level in a day, and in a day there's only 24 hours, and then it starts repeating. Okay. What's the amplitude? So you're going to look at this highlighted thing, and you have to pick out what the A value, the B value, the C value. So be careful here. What's this 12 sitting out front here? Usually they don't put it out front. They did it here to trick you. Usually they would have 5 sine, all this stuff, plus 12. This is your D value here. This is your A value here. D, A. This is your B value. This is your C value. So the amplitude, well, the amplitude is just the absolute value of A. In this case, the absolute value of 5, so it's 5. The equation of the midline. Midline, you look to D, and it's 12, so that means it's y equals 12. Maximum minimum depths, oh, you can use this information here. If the midline is at 12, right, here's 12, and the amplitude is 5, means it goes up 5 and down 5. How high does it go up to? 17. How low does it go down to? 7, right? 12 plus 5 is 17, and 12 minus 5 is 7. So there's your answer, maximum, minimum right there. Determine the period. Well, to get the period, you do 2 pi divided by the absolute value of b. So that's 2 pi divided by the absolute value of 0.524. So just 0.524. And if you do that, I don't feel like showing you on a calculator, it equals 12. Try it yourself if you want. Use a graph of the function to determine the depth of the water at 2 o'clock. So we actually have to graph this. So we're going to go back to Desmos and plug this in, get rid of these things, and put y equals 12 plus 5 sine 0.524 x. I think you can put t, but I'll just call it x, plus 1.571. And there you go, and I don't see anything. That's because, yeah, there it is up here. Actually, I'll just do that. Rather than using the windows up here, I can just scroll around. It's nice. And we're interested at the water depth at 2 o'clock p.m. Remember, time is number of hours after midnight. How many hours after midnight is 2 o'clock p.m.? Well, noon is 12 hours after midnight, and this is another 2, so it's 14. The t value is 14. So we'll go to Desmos and we'll put x equals 14. There's where it crosses, and that's 14.475. Let's call it 14.5. So 14.5 meters. A ship that requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest necessary 10 minutes must it leave to prevent grounding? So water can't go below 8.5. So this is a y amount, right? The depth is y. So y equals 8.5. So at midnight the water is at this height, and that's no problem for the boat, and the water level is going down, it's going down, it's going down, no problem for the boat. But once you hit this point, the boat is in big trouble. So that's after 4.48 hours. 4.48 hours. Well, the 4, obviously that means 4 complete hours. So 4 hours after midnight is 4 a.m. So we'll put 4. But this 0.48, what's that all about? Well, that's 0.48 of an hour. Each hour has 60 minutes. If I multiply 0.48 times 60, I get 28.8. So let's round it to 29, I guess. At 4:29 a.m., it has to be gone. Now they've thrown a little wrinkle into this question. It says, by what time to the nearest necessary 10 minutes? So what a lot of people will do at this point is they'll say, well, the nearest 10 minutes is 4:30. He can leave at 4:30. Is this true? No, at 4:30 it's too late. Remember, he has to be gone by 4:29. So the actual answer they want, which I know it'll be amusing for some of you, is 4:20 a.m. Although I don't know if the 4:20 rules apply in the morning. But anyway, there you go. What's the next time to the nearest necessary 10 minutes that the ship can safely return to the harbor? So here we go. He's gone by this point. He's out in deeper waters, but he wants back into the harbor. When can he come back in? Right here. This is where the depth of the water is deep enough again. So that's after 7.51 hours. 7.51 hours. This is hours, right? Same here. This is hours. Well, the 7 hours means it's 7 in the morning, but we got to figure out the minutes. So 0.51 this time of an hour. So that's 0.51 times 60, 630, 30.6. So let's call it 31. At 7:31, he can return. So again, we want to round this to the nearest 10 minutes. And again, what a lot of people are going to say is the nearest 10 minutes is 7:30. But at 7:30, can he come back in? No, the water level is not deep enough at 7:30. So he's actually going to wait all the way to 7:40. If he's going to go to the nearest 10 minutes, and that's 7:40 a.m. Okay, there you go. We have now completed Chapter 5.